And now that we've seen some kind of brief overview of why we would use the analysis of variance, then now let's talk a little bit more about what it is. Now the analysis of variance at its core is the F-test, and sometimes when you say ANOVA, that's all you mean, just the F-test. So that's what we're going to talk about mostly here. So the analysis of variance is a process whereby we can test multiple hypotheses kind of at once, but we're not really cheating because we test them all at once, but we don't get that much information out of it. Sometimes that's all the information we need, but often we need to follow up and get some extra information after we're done with that. So the hypotheses in the analysis of variance follow the same pattern of hypotheses that we've seen elsewhere. You have a null and you have an alternative. In a single sample T, your null hypothesis is that the mean that your sample came from, so the population mean of the population that your sample came from, is equal to some value of the null hypothesis that you, like the null hypothesis implied value that you've gotten from elsewhere, so an outside population mean or some intuitively satisfying value, something like that. With a two-sample T, then we switch to the null hypothesis being that the two groups are the same in the population. So in your sample they're never quite the same, but your hypothesis is that in the population at least these two things are the same. And then with the analysis of variance, our null hypothesis is that however many groups we have, and it can be any number, although realistically it's never more than about a handful, however many groups we have, the population means that each of the groups came from, though the means of each group's populations are the same. In other words, the groups came from the same population, so there's nothing going on, there's no difference, there's no effect having. And sometimes we'll say all the population means are equal, or sometimes people will say there is no variation among the population means. Now this last one, there is no variation among the population means, that's the most closely aligned to the math that we actually do. So let's talk about what that math is. So here we've got a situation where we've got these three groups. Group 1, Group 2, Group 3. Each of them has a mean, and each of them has some variance within the group. And we've seen this before, but let's just kind of keep going. Repetition helps us learn things sometimes. So each of these groups has a certain amount of within groups variance. We could measure that with a standard deviation or an IQR, but we're going to use the variance to measure it because the variance has these lovely mathematical properties that are beautiful and pure and interesting to mathematicians. They help us build other things later. So we're going to use the variance, within groups variance. We're going to average that within groups variance together across however many groups we have. In this case I made it 3, but it could be any number. It could even be 2. It just can't be 1. And then we're going to come up with an average or pooled within group variance. Pooled just means averaged. So this is the average variability within each group. That's our estimate of sampling variation. That's our estimate of what we call error variance. And it's error because it's kind of our error. It's error because we don't know where it came from. We can't explain it with our theory. And then we come up with an estimate of the variability among just the means. We treat each mean as a single observation point. We come up with the grand total, the mean of the means, which is really just the mean of all the data points together, as if you took away all the group divisions and just added up all the data points together and divided by the number of data points there are. Anyway, it's the mean of the entire study. So the mean of the means, the total mean, the grand mean, we look at deviations from that, and that tells us about between groups variance. So that's variance between the means in your sample. And then we compare that ratio. We look and see, is the between groups variance a lot bigger than the within groups variance? And if it is, then we reject the null hypothesis and we say, hey, this is not what we would expect if the null hypothesis were true. If all these group means were the same in the population, we would not expect their variance, their average differences from each other of the means in the sample to be bigger than standard, just regular sampling variation. So, without some details, we calculate the between groups variance, sometimes shown as a sigma squared sub b, sometimes s squared sub b. And to do that, we treat each mean as one data point, and then we just calculate the variability among those group means. We have to figure out what the grand mean is first, because whenever you calculate a variance or a standard deviation or something, you need to know what the mean is first, because it's the average deviation from the mean. Well, you need to get the mean of the means, so the grand mean or the total mean. Anyway, you calculate the variance from that. And then you calculate the within groups variance for each of your groups. Now, however many groups you have, you do this that number of times. And so that's just the variance of regular observations, not means or anything funky, just the variance in each group. And it's just the deviations, the average squared deviations from each group mean, and you average them together. And then you compare the between groups variance to the average within groups variance. One of the classic ways to compare things like this is to divide one of them by the other. So we divide the between groups variance by the within groups variance. And that's how we determine, and that gives us one number. And of course there's a sampling distribution of that number. And that's how we determine whether we think the difference in between means was greater than can be explained by sampling variation alone. So if that ratio of between groups variance to within groups variance is big enough that it would be unexpected under the null hypothesis, then we reject the null hypothesis. We say this is unlikely if the null hypothesis were true, therefore we reject it. So it's all about this ratio. Between groups variance divided by within groups variance. The between groups variance is the apparent effect. It's what looks like is happening that we're interested in. And we say apparent because anything in our sample is apparent, and we don't really know how well it reflects the population. That's what this whole process is about, trying to estimate that. And we kind of keep it honest by comparing it to the estimate of sampling variation, and that's the pooled within groups variance right there. So how big is big enough for that ratio? Well, we need a sampling distribution. That ratio reduces the between groups variance and the within groups variance to one single number, right? Because you divide one thing by another thing, you've got one number. And there's a sampling distribution of that number. That number is called f, and there's a sampling distribution of f, the sampling distribution of the ratio of the between groups variance to the within groups variance in any given situation. If the null hypothesis is true, then the expected ratio of between to within groups variance is about 1, more or less. It's not quite that simple, I don't think, but it's about that. In other words, they're kind of about the same size. If you divide something by itself, then you get 1. So these things are approximately the same size. Now, it's not quite as simple as just saying it's 1, but if you get a ratio that's close to 1, you know you're not going to find any significance there. So the expected value under the null hypothesis is generally about 1. But it depends on degrees of freedom, etc. How many groups you have, how many observations you have. So what are all the possibilities? Not just the expected possibility, like the mean, but actually now you're going to see why we don't say mean anymore, we just say expected value. What are all the null hypothesis possibilities for this ratio of between to within groups variance? Well, that's the sampling distribution. The sampling distribution of that ratio of variances if the null hypothesis were true. And so then in that sampling distribution, we just plug our observed between to within groups ratio into that distribution, and we calculate the area beyond it. So you've got what we call the sum of squares between. We'll talk a little bit more about this. The sum of squares between groups divided by the degrees of freedom between groups, that's the variance between groups. So any variance formula, the numerator part that has the sum of x minus x bar squared, etc., that's called the sum of squares, the sum of the squared deviations from the mean. And then the denominator that says n minus 1, that's the degrees of freedom. So we've got the variance in green there between groups, and in blue there within groups. We call those variances mean square, MS. I don't know why, it's just leftover old terminology. In ANOVA you have terminology that was formed in the 1910s or the 1920s or something ridiculous, and nobody's ever changed it. It's just variance. It's just the variance estimate for the variance between the means, or the variance estimate within the groups. Well, you divide one of those things by the other thing, as we've mentioned, and the result we call f. So f is like t, actually. In fact, if you only had two groups and you did an analysis of variance, f, and then you also used those same data and did a t-test between those two groups, the f would be exactly the squared t. Not that you need to know that, but it just shows you that we're dealing with a similar kind of stuff here. Anyway, f is the ratio of between groups to within groups. And what we actually found in our study will be F observed. And so there's an F observed, and there's an F critical as well. So our F observed, we're going to calculate that. And that's kind of a pain in the butt. We won't do it too much, but we'll run through it a few times to make sure that you know how to do it. Not that you're going to do it much in your lives, computers will do this, but because it's important to do it so that you kind of start to get a feel for what's actually happening here. I think that's important. So this F observed here, the distribution of F is always horribly positively skewed like this. Like the T distribution, there's an infinite number of F distributions, and it depends on the degrees of freedom in your study. And in fact, there are two different sets of degrees of freedom. Now there's a degrees of freedom for the between, which we call the degrees of freedom for the numerator, and degrees of freedom for within, which we call degrees of freedom for the denominator. So you have to always know how to figure out your degrees of freedom for these two things. Because that's how you look up the appropriate F distribution to look up your critical value. So we find our F observed, and just the area beyond it is the p-value. That's it. Now if you have a computer, that's all you do. You just find F observed, calculate the area beyond it, p-value. But of course there's so much different data here, just like the T, but even worse, that nobody ever gives you an entire F observed table that shows you actual p-values for all the F observeds you could find. You'd need an entire huge book of F tables for that. So instead, they just get like a couple of pages of an F table, like the one that is provided for you in Angel, or it's provided for you online. You just find a few critical values. So you find a critical F, and you compare your F observed to your critical F, to see if F observed is greater. So what is P? It's the same thing it always was before. P is just always the probability of observing a result this big. Now the result in this case means a ratio between subjects, or sorry, between groups variance and within groups variance. It's the probability of observing something this big or bigger if the null hypothesis is true. So we took what we observed, and then we just calculate the area and the tail beyond it. So it's always to the right. There's no more two-tailed, one-tailed business here, not with F. It's asymmetrical, and it always goes to the right. So if P is less than alpha, and of course we set alpha at 0.01 or 0.05 or 0.001 or something, then we reject the null hypothesis. So ANOVA has lots of little parts, and we organize those little parts in an ANOVA table, sometimes called a source table. And you're going to need to learn how to construct it and how to fill it in. Even though when we see it getting spit out from a computer at us, we usually only care about this one little part, the p-value. So this is what it looks like. It has all these pieces in it. These are all the pieces. So you've got the sum of squares between and within, and degrees of freedom between and within. This total business, you don't have to worry about that. It gets done by some software. Some software doesn't bother with it. It's something we used to do when we had to do this all by hand all the time. So the mean square is this divided by this, and then that gives you the variance between and the variance within. You divide this by this, you get the F ratio, you look that up in a table, and you get the p-value. Actually, you probably just find out whether p is less than alpha or not, because the table doesn't have information any more specific than that. But the sum of squares, that's the core of ANOVA. That's where the machinery happens. That's the heavy lifting. And calculating those sum of squares is actually the most annoying and slightly complicated part of doing an analysis of variance by hand. But that sum of squares, that's the core of a variance, therefore it's the core of the analysis of variance. This sum of squares total and degrees of freedom total that's left over from the olden slide rule days, it is kind of neat because in a between subjects analysis of variance, which we are going to be doing in this class, this plus this equals this. So it was a way to check your math and make sure you've done your math correctly. So sum of squares between plus within equals total. And actually the degrees of freedom add up too if you did it right. Degrees of freedom between plus degrees of freedom within equals degrees of freedom total. Now here's where the action happens right here. The action happens in variances. Once you get a variance, a sum of squares divided by its degrees of freedom, then you have a variance. Now you've got the between and the within subjects variance. You divide those by each other, you have the F ratio. That's our point estimate. So we're taking the F ratio from our sample, and we're saying what's the likelihood of finding an F ratio this big or bigger if the null hypothesis were true. So that's our point estimate. Let's see how complicated this got. Our first point estimate was a mean, and then we have like a difference between means, and now we've got this crazy thing that's our point estimate itself is the ratio of the difference between two variances. It's kind of complicated, but it actually works very well. And then the p-value is the really important part. Now, most of the time you'll just be looking at this stuff coming out of a computer, and every computer system will give you the information in a slightly different way. As you know, SPSS calls p sig for some reason, because they're just too fancy to change for anybody. So anyway, that's the really important part. And then the degrees of freedom, that's the equalizers. That's how you take the sum of squares and turn it into sum of squares per observation or per group or something like that. Anyway, that's the stuff you put in there. The only real difficult calculating part is these two sum of squares. Degrees of freedom, there's a very simple formula to figure out what those are, and then after that, everything else just gets done in your formulas. It's done in the table. So the sum of squares is the heart of ANOVA. That's the numerator of any variance formula. So there's variance, and the numerator here is the sum of squares. So this is how you calculate just standard regular old variance in a data set. The numerator is the sum of squares, meaning the sum of the squared deviations from the mean. The degrees of freedom, that's what makes sum of squares into a variance. That's the equalizer. That's what takes the sum of the squared deviations and turns it into the average squared deviation. Not just the added up squares, but now the average, because the average is add stuff up and divide by n, right? So we added up some squared deviations, we divided by n, now it's average squared deviation, because we want to compare apples to apples, oranges to oranges, so we need that. And that's the denominator of the variance formula. There we go, right there. So with regular variance, it's n minus 1. And actually, we'll keep following that pattern here. Just a quick hint, we'll do variance for each group, and that'll just be a standard variance. And then we'll add those things together. And that'll be our within subjects variance estimate there. But the between subjects variance estimate, what we're going to do is we're going to take each mean of each group and pretend like it's just a simple observation. So each of these will be a mean now, and this will be the grand mean for the entire study. And instead of n minus 1, we'll say k minus 1, because k is a number of groups. So it's the same idea. We'll just use different symbols to express the fact that we're doing this with means instead of with individual observations this time for the between subjects business. But we'll get into that later. So the degrees of freedom, in general, degrees of freedom for any particular part of this analysis is the number of data points considered minus the number of population parameters being estimated. So the degrees of freedom for the between subjects portion is k minus 1, the number of groups. So k is the number of groups minus 1. So k in this case is like an n, but it's an n for entire groups, not for individual observations. And the grand mean is estimated as part of estimating that variance between groups, and so we have to do the minus 1 to account for the fact that we already estimated a parameter, and so we don't want to double dip here and double estimate. And the degrees of freedom within is the total n minus k. So in other words, it's n minus 1 plus n minus 1 plus n minus 1 plus n minus 1, however many groups we have. Or another way to think of it is all the n's added together for each individual sample, and then k, because that's the number of groups you have. So if you have 3 groups, n minus 1 plus n minus 1 plus n minus 1, that's the same as n plus n minus 3. Same thing, just flipping things around mathematically. Anyway, there's little formulas. K minus 1, n for the total study, minus k. That's how you figure out your degrees of freedom. Easy peasy. You put it in your table. There you go. So here's an example with some numbers, which you'll see come back to haunt you in future examples. Somebody calculated the sum of squares. There they are. Hooray, how amazing. Oh, now we have our degrees of freedom. We figured that out. Actually, you probably did that before the sum of squares. The sum of squares divided by the degrees of freedom gives you the mean square. And that's your variance estimate. Mean square is variance. Remember, that's the weird word that ANOVA uses. ANOVA has its own language, which it shouldn't. It's very silly, but it does. And then sum of squares within divided by the degrees of freedom within gives you the mean square within. Now the F ratio is the mean square between divided by the mean square within. So if you've been looking at that table, you already see it's going to be pretty easy to get that now that you've got the sum of squares. The sum of squares is a little fussy and takes a bit of work by hand. It's not difficult work. Nobody has to do any differential calculus. You just have to add some things up and divide some things. That's all. But the F distribution, sampling distribution of the ratio between two variances, our F observed goes in the ANOVA table, and we look at an F critical, which is the critical value that we have to surpass so that we will believe that our F observed is bigger than random sampling alone could explain if the null hypothesis were true at a particular alpha level, 0.05 or 0.01 or something. And F ratios are asymmetrical, so they're always one-tailed, which is kind of nice. And now let's just look at an example of an ANOVA table here. This stuff is kind of filled in. 30 divided by 2 is 15. 209 divided by 45 is 4.64. So the estimated variability between groups is 15, and the average variability just between individual data points, so the within groups estimate, sampling variability, is 4.64. You can see this is big and this is small. It's probably going to be pretty big. This is like 3 times, well, almost 3 times as big as this. So you divide those by each other, and we get the F ratio, 3.23. Is it big enough? Well, F critical for 2 and 40 degrees of freedom at alpha of 0.05, if I look this up correctly, is exactly 3.23. So we can say, yeah, P is essentially 0.05. So we can say, well, I guess I chose to say it doesn't quite make it because it was equal. You could say there was no statistically significant difference between the groups in whatever the response variable was. And then now you have to just put a whole lot more stuff in those parentheses. You have to put your, well, not a lot more stuff, a little more stuff. You have to put 2 degrees of freedom now, 2 and 45. See, 2 and 45. And you can figure out the number of observations and the number of groups here. 2 degrees of freedom means there were 3 groups. 45 observations means there were 48 total observations in the study. Sorry, within 45 degrees of freedom within means 48 total observations in the study. So you can reconstruct quite a lot about your study from looking at an ANOVA table. I'm going to stop right there, and then we'll get into some more details later in future lectures. So watch this 100 times if you need to. It's just a lot of new information. It's not a massive mind flip like some of the other stuff we had, but it is new.